I'm going to try to review the terminology that we're using here in Chapter 6, especially at the beginning of Chapter 6. So hopefully after a few days of doing these kinds of problems that the terminology becomes second nature to you. So let's start with an f of x equaling 2x. And you can represent the family of all antiderivatives of this function f of x equaling 2x by, let's say, defining g of x to be x squared plus c, where c is a constant. The constant c is called the constant of integration. The family of functions represented by g is the general antiderivative of the function f, and g of x equaling x squared plus c is the general solution of the differential equation g prime of x is equal to 2x. Okay, so remember we have a differential equation, and the general solution of the differential equation is given to be x squared plus c. Okay, a differential equation in x and y, again, is an equation that involves x, y, and derivatives of y. For example, y prime equaling 3x, y prime equaling x squared plus 1, are examples of differential equations. Okay, so then we talked a little bit today about slope fields, and if you remember that the line segments, well, a slope field consists of line segments with slopes given by the differential equation. The line segments give a visual perspective of the slopes of the solutions of the differential equation. Okay, so the derivative, the differential equation, could depend on just x, just y, or as you see down here in number 3, both x and y. So we did a couple examples in class that involved just x, and then I want to do an example right now and do number 3 together, and then I want you to do the rest of these on your own, and then you can check the solutions. I'll show those after a brief pause. Okay, so if we look at let's see, let me get a different color for my slope field. Let's use purple. Okay, so if we just choose a couple points, we choose, let's say, 0, a couple values for x and y. 0, 0, we know that 0 plus 0 is 0, so y prime is equal to 0. So nothing fancy there. So we're going to draw a line segment with a slope of 0. And then we would do the same thing for all the points. 1, 0. The slope would be 1 plus 0 is 1. So we draw a line segment there at the coordinates, at the point 1, 0, that has a slope of 1. And then let's pick 2, 0. 2, 0, the slope is 2. So we aim towards this guy right here. Remember that? We aim up 2 and over 1. So if you aim there, you can get a better, maybe a, oh, that's pretty good, I guess, a better accurate line segment. Okay, and then we try 3, 0, and we get 3, so we don't really have another dot down here or anything, but we can just make sure it looks steeper than the one just before it, because this one has a slope of 3, slope of 2, slope of 1, slope of 0. Okay, so we're going to need a little bit more room for our x, y, and y prime chart. So let's build that over here. So basically you would do the same thing for all these of these different points. And yes, this is tedious, but you start to see patterns. Okay, so it gets a little bit, you get a little bit faster at it after you do it for a little while. Negative 1, 0, we have a slope of negative 1. Negative 2, 0, a slope of negative 2. So you can see it starts becoming a little bit easier. Negative 3, 0, the slope is negative 3. Just make it a little bit steeper than the one just before it. Okay, let's see if we can see a pattern here in the row here where we've got y equaling 1. So if we start with 0, 1, 0, 1, we know that that's 1. So anytime the x and the y differ by 1, or add up to 1, then the slope is 1. It would be 2, negative 1, 3, negative 2, negative 1, 2. So all those have a slope of 1. All those along that diagonal. See if we can find some zeros. Anytime, that's another good way to do it. Just look for patterns. When are we going to get 0? We're going to get 0 when x and y are opposites. Okay, 1, 1, the slope is going to be 2, so that's not opposite. Negative 1, 1. Negative 1 and 1 are opposites, so we have slope of 0 there. Negative 2, 2 are opposites. 1, negative 1, 2, negative 2, and so forth. Okay, where are we going to get a slope of 1? I already did that. Where are we going to get a slope of negative 1? Well, we get a slope of negative 1 when we have, let's say, negative 2 and 1. That's a slope of negative 1. Negative 3 and 2, slope of negative 1. 0, negative 1, add those together. 1 and negative 2, add those together. So those are all slopes of negative 1. Okay. And then what happens if we add negative 1 to negative 1? We get negative 2. Okay. Negative 1 to negative 2 is a negative 3. Okay, negative 2 and negative 1 is negative 3. So all three of these are negative 3's. Negative 2 and negative 2 is negative 4. So it's almost vertical on these, so just make sure they're steeper. So 1 is steep, and then steeper yet. So you just keep adding. 1, 2, 3. Negative 3, 1 is negative 2. Okay. And then what do we have? 1, 2, 3, negative 1, so that's a 2. And then so 3, 1 is a 4. 3, 2 is a 5. 2, 1 is a 3. 2, 2 is a 4. 1, 2 is a 3. Okay, so there you get the general idea of how to construct a slope field. And so what I want you guys to do to get some practice on this is, I know this is a little bit tedious, but I think it definitely would be a worthwhile venture for you to draw a few slope fields, and then once you draw a few slope fields, then all the rest of the slope field questions actually tend to be pretty easy once you know how to draw a slope field. So this is number one priority, is that you learn how to draw a slope field. But well, we'll talk about that one as soon as I show you the solutions to this page. Then we can talk about some patterns that you can see. Because if you look at the second page, you're going to have to match slope fields with their differential equations. And so this is another type of slope field problem that you'll get to do. And these are actually kind of fun. They're like little puzzles. But anyway, pause the video, show or do the problems, and then I will show you the solutions, and we'll talk a little bit about the solutions and how you can find some patterns from those solutions. So go ahead and pause the video. Here comes the solutions. You can pause the video as you correct your own, because I'm just going to scan right through these. There you go, 1 and 2. There we have 3 and 4. And there we have 5 and 6. Okay, so here's the thing I wanted to talk about. Look back here at number 1. Number 1, notice that in each one of these columns, the slopes are exactly the same. Okay? So every single one of the columns, no matter what the y value, when you get to one x value, you get like negative 1, all the slopes are 0. When x is negative 2, all the slopes are negative 1, and so forth. So when you see columns like this in which all of the slopes are the same, then the slopes don't depend on y. Okay? The slopes do not depend on y, and if you can kind of grasp that concept, then when you're matching a slope field to a differential equation, the only slope fields that wouldn't depend, where the slopes don't depend on y, aren't going to have a y in the differential equation. In other words, dy dx will not depend on y. Here, dy dx only depends on x. So that's why you see in the columns the slopes are all the same. Okay, it's a good contrast here. Problem number 2 is a great contrast to problem number 1. Notice here that as you move down any column, the slopes are changing. The slopes of all those line segments are changing. Therefore, the dy dx does depend on y. Okay, but if you also notice here, the slopes as you go from left to right across any one y value here, the slopes stay the same. So the slopes stay the same no matter what the x value is. Okay, and for any one y value, you've got the slopes staying exactly the same. So in other words, the slopes in this slope field depend only on y because they are independent of the x. Okay, independent of the x meaning that the slopes are all the same in each row. Independent of the y, the slopes are the same in each column. So you can see, first one has only an x, dy dx only depends on x, and dy dx in number 2 only depends on y. Okay. So again, this is helpful when you're trying to match a bunch of slope fields to a bunch of differential equations. So gives you a little bit of a way to well, what am I trying to say here? It gives you a way to weed some of them out, so to eliminate some of the possible answers. Okay, I didn't want to pause the video there. So anyway, number 3, you can see that no matter what the x and y are, no matter what row or column that you're in, you've got the slopes are all changing. Okay, so the slopes are changing from left to right, up and down. Therefore, the dy dx would depend on both x and y. Okay, so something to look for as we go to page 2. And I'm going to go ahead and stop the video and pick it up again in the next video for page 2.